main thing I want to do today is derive the minimum variance estimator using conditional random variables. It's a totally different approach to the problem. And hopefully get us more comfortable with the idea of one random variable being correlated to another, and if you measure that second one, that gives you information about the first one, and perhaps moves this mean over, shrinks down this variance, and things like that. That's what I'm certainly that's what I want to go away with feeling good about. If you have that, the Kalman Filter is straightforward. It's a little technical thing, but it's really the minimum variance estimator. So, I kind of challenged you to read a little bit of the key points from the summary, and we answer questions. So should we start with the Q&A on the what is the probability, continuous, random variables having density? Where are you having problems conceptualizing randomness? For you, it's all deterministically easy, right? No randomness in your knowledge of random variables. You don't even know enough to ask a question? Do you even hazard a guess at a question? Okay. Anti-glare. Well, okay. It'll be boring if I just kind of read it to you. We have random variables which are not interesting enough for an engineer because we need something and something of measurement. We need at least two of those. We're working with vectors almost all the time. So a random vector is just something where each of the components is a random variable. Things that are random could be like dice. They can be discrete, or they can be like the infamous Gaussian distribution and be continuous and have a density. So we're working with things that have a density. And the definition is that if you look at a very simple type of event, set of all points with your probability phase where the random vector component-wise is less than x1, x2, xp, you get that by integrating the area under the density. And so as these guys tend to infinity, you integrate the entire density, you get 1. So in principle, all the calculations involve lots and lots of intervals. We're going to be focusing on Gaussian random vectors where they're really defined by a mean and a covariance. So we can propagate that information. We know everything. We aren't propagating the complete density. So the mean is the expected value. That's when you integrate x against the density. And so physically it represents you sample, you measure, and the state hasn't moved. You're just seeing the noise in the sensor, measure, and you average all of those. That's the mean. Okay? Now you take all those measurements and you mean minus the measurement squared, and you add all those up and you divide by n minus 1, you'll get the variance. That's an unbiased estimate of the variance. You divide by n, and n is a 500,000, it doesn't matter that it's n minus 1, okay? It just doesn't matter. So that's the spread. So your points are kind of a cloud here, and that's the spread, the variance. So you'd like that to be small, if you have a good estimate. In principle, it's the average value of x minus the mean, times x minus the mean transpose. You have a vector, and that gives you the variance of the first component of x, the correlation of the first component of x and the second component of x, etc. It gives you all of the correlations on the off-diagonal terms and the variances of the individual random variables on the diagonal. So that's the covariance. Those are the two most important moments that we work with in Robotics. Good mean spread. Yeah, they're really giving me the cold shoulder today. Okay. Conditioning. So this is what you do when you have measurements related to another quantity. A is some event you care about. For us, it's going to be some state that we care about. And B is the information coming from a measurement of A. So in probability, the conditional probability is defined by the probability of A intersected with B over B, which I want you to mentally think about as the joint probability of A and B divided by the marginal. Okay, those terms that we introduced for vectors, joint over marginal. And just measuring something does not make it no longer random. So A conditioned on B is still an event, and this probability is this conditional probability. P of the joint over P of the marginal. So I just wanted to think about it that way, so that when we get to densities, you have that in your mind. So we take a random vector, and I fixed the typo that I had here. It has n components and m components. We just break up x up into capital X1, capital X2, kind of a fuse notation. So this is now a vector, not a single component. This is now a vector. And then the density of this vector, since we're now thinking about it in terms of these two components, we call the joint density of x1 and x2. But it's still just the density of a random vector. It's just a name because now we're focused on x1 and x2. In applications, this is like the position of the robot, and this is the measurement from a LiDAR or camera or a wheel odometry, encoders, things like that. And so the things that are connected, and we stack them all up together because this will have a mean and a covariance, this will have a mean and a covariance, and then they will have a correlation. Okay, that's all information that's in the density. Okay, so it's just the density of x, but we call it the joint density of x1 and x2 because it has all the information about how x1 and x2 are related, all the correlations. And then if we just integrate out the x2 variable, we get the marginal, just the density of x1 as a random vector, and we can get the density of x2 as a random vector. And then we say that these two random vectors are independent when the density factors. And marginals in principle are integrals like we did in one of the or two, I think it was, but whatever, we will not be doing any integrals like that on the final exam. I don't care about your ability to do calculus. I hope it's good, but I'm not going to be testing your calculus specifically because all it is to do those calculations. They're really tedious and they're really boring. The most important thing we have is this notion of a conditional density. I want to play with that a lot today. So x1 and x2 are components of a random vector, meaning you know how x1 and x2 are related. We have the joint density. I now measure the second component of a big vector, and I get a value. And I want to understand what that tells me about x1. So we define the conditional density of x1 given x2 equals x2 as the joint over the marginal, and the marginal and the joint, the x2 value is this one. So if you put a bar here, you put a bar here, or you put a bar there. That makes it more clear to you that x2 is a number that I got out of my LiDAR or camera or encoder. I hope that helps, okay? So now, as I change the measurement, I do change this density. And it will often write x1 conditioned on x2 is distributed or has density, and then this is the marginal density. This is the joint, this is the density of this is the conditional density, it's the joint over the marginal. So probability of A intersected with B over probability. That's what we have here. Use shorthand notation. Just because the formulas get heavy, but we know that when we're doing this, you always have to keep in mind that there is a value. There is a value. Now, it may be a variable in your problem because you haven't made the measurement yet. You're just putting symbolically x2 there or something, but it's still there's still a variable. And the key thing is, just because I measured the second component doesn't make the first component no longer random. It's still random. Okay? It's still random. It's still uncertain. It still has a mean and it still has a spread, but that mean has shifted because I've made a measurement related to it unless they're uncorrelated or independent. And the spread is probably reduced. So that's what we want to understand better today. It's still a random vector, and this is its density, x1 conditioned on x2. Okay, just like the probability of A given B, it still has a probability A intersected with B over probability. Joint over margin. Okay, you guys did this in your homework. I'm going to come back to it a little bit later. Are there questions on this first part? We're going to work some examples using it, but questions are good. Yeah.
Is it possible to condition on a variable and have uncertainty increase?
I don't think so. Let me not say it because I'm not sure, but I don't think so. Okay. All this, when we do the normal random variables, it can never increase. Sure, I would say that, yes.
I think it can't ever because in the formula, you take the original covariance and subtract some quantity, and that quantity has to be positive because all of your covariances also have to be positive.
Yeah, so I think the only question is exactly what you mean by uncertainty. So Gaussian is really clear. You just have the sigma 1, 1 minus something. So the Gaussian case is always reducing. And I think it's true in general, but I'm not enough for probable. Yes?
Are you always dividing by the rest?
Right, always dividing by.
Yeah. So.
Yeah, so if that were 0, there'd be a problem, right?
Yeah. So it has to be.
Yeah. So that's the whole idea. I mean, this should be, just like when we define the conditional probability of A given B, if the probability of B is 0, this makes no sense. So you need that. When you do the density, I'm sorry, you do the density, you need this thing at x2 to be non-zero. So you're doing a uniform distribution from 0 to 1 and we measure to 3, the density would be 0 at 3, okay, to be a problem.
Can you just repeat what she asked? Because I didn't hear.
Yeah, I'm sorry. So she was pointing out that probably the uncertainty has to decrease because we're dividing by something less than 1. I think that was the main point. Yeah. That's not perfect. I was agreeing. Others? Yeah.
I think there is no limitation that the density function has to be less than 1.
Wow.
There's one.
Okay, let's take that as a challenge problem for the class to report back on next time we meet, okay? Let's go and get this minimum variance estimator going. But okay, so the question is, when you condition, can you ever cause the variance to increase? I don't know. Okay. For Gaussian, no. Others, I don't know. I should. Oh, you're right. Unhappy people. Sorry, I was too excited to start the lecture and didn't turn on the mic. Thank you, Sabrina. Does that help you a little bit hearing too? Yeah, yeah. Okay, so we'll go through this conditional stuff a little bit later. Let's revisit minimum variance estimation and use the techniques that we've just looked at. Okay? Now I'm going to use things about normal random variables. I'm just pointing out here, our solution, we never said anything about Gaussian and normal. We just said we had a mean and a covariance. So it applies to anything, Laplace, whatever, okay? It makes no difference for the solution we did using the projection theorem. It's extremely general, extremely general. So that's nice. Okay, but here's the problem we had. And what am I doing differently? Well, okay. I'm going to choose a particular density for X, and I'm even going to allow it to have a mean. What the heck? We said zero mean when we did our problem on MVE. I'm going to choose a density for the noise on my measurement. Okay? I'm going to choose normal as well. So this is a covariance of X. This is a covariance of epsilon. I'm assuming each one of these are positive definite. These are the mean vectors. So that's what that means. And then just like we did in MVE, though you'll see it's not that important, I'm going to assume that X and epsilon are uncorrelated. Now, since I've said they're Gaussian, they're also independent. But, you know, when we solved the problem before, we had this condition, uncorrelated. So that just means that whatever is causing the uncertainty in, for example, where the robot is, that has nothing to do with the uncertainty of measuring how long it took the light beam to go to the target and come back, okay? The fact that you lost your robot doesn't affect physics is what that says, okay? That's all that says. They're uncorrelated because of that. So let's calculate first the statistics of y. Okay? So, whoops. The mean of y is equal to what? Well, it's the expected value of c times x plus epsilon. So that's c times the mean of x plus the mean of the noise. So it's c mu times x plus mu of the noise term. So that's the mean value of the measurement. We just use linearity and the fact that expectations are integrals, constant comes out, expectation of a sum of the expectations. Good? Let's calculate the covariance of the measurement. Okay? So I'm going to call that sigma yy. So that's the expected value of y minus its mean times y minus its mean transpose. Okay, so what is that equal to? Okay, first of all, y minus its mean is just c times x minus its mean plus epsilon minus its mean. Okay, so that's a really quick calculation just to plug in for the average value of y and subtract it out, okay? So then what does this product, y minus its mean times y minus its mean transpose look like? Okay, so let's just form y minus mean of y times y minus mean of y transpose is then equal to the vector c times x minus, it's at least minus the mean of x plus epsilon minus the mean of the noise term times that thing transposed. Okay? C times x minus mu x plus epsilon minus mu epsilon transpose. Okay, so what do we get when we multiply these two things out? So this transpose gives us x minus mu x transpose c transpose. So that multiplies this. So let's see if we can just agree that this is x minus mu x times x minus mu x transpose c transpose. That's the first term. Let's go ahead and throw in these two terms and then we'll do the cross terms. How about that? Okay. So we have epsilon minus mu epsilon times epsilon minus mu epsilon transpose. Okay, so then we have this term times this thing transposed, and then we have this term times this one transposed. So we end up with c times x minus mu x epsilon minus mu epsilon transpose and epsilon minus mu epsilon times x minus mu x transpose c transpose. Okay, so that's the messy computation of getting y minus its mean times y minus its mean transpose. Just plugging in everything. Now we should take the expected value of that. Okay, so the covariance of y is just equal to expectation of this. The expectation of this, we take the expectation inside the constant matrix, and we take this one out, and what is the expectation of this term? That's that sigma xx. That's just the variance of x, okay? This is the definition of the variance of the noise, epsilon, okay? What is this term? Yeah, that's the correlation between x and epsilon. We've assumed that's 0. And then we have the correlation transposed, okay? So, expected value of, no, let's write it down this way, sorry. Let's just write it down this way. Covariance of y, which I'm going to call sigma yy now, is equal to c sigma xx c transpose plus sigma epsilon epsilon, and then plus 0 plus 0. Just to recognize that we check this term. This is sigma x epsilon, and this is sigma epsilon x, and then the c transpose, okay? So that's the covariance of y. So when we solved the minimum variance estimation problem using the normal equations, this was the Gram matrix. This is the Gram matrix. We had C, P, C transpose plus Q. We called the variance of X P, and we called the variance of the noise Q. We had C, P, C transpose plus Q. Our assumption was positive definiteness. Okay? So That's the Gram matrix. It's all the stuff that we did with the normal equations, it's showing right up. Okay, everybody comfortable with how you get the mean and the covariance of y? Okay, now let's start building up our estimation problem. I'm going to define, and when you solve the mystery of can we increase uncertainty by making a measurement, also find out how I can turn off this zooming command in this PDF program I'm using. Okay, I'm going to define a big vector x. And it's going to have components x and y. Okay, so this is our unknown x, and this is the measurement, and we just computed its mean and its covariance, okay? So the expected value of this great big X, that's easy. That's the mean of X and the mean of Y. Okay, now, what is the covariance of this random vector? Covariance of X. Okay, you guys are starting to get the hang of it, but let's just mentally do it. I mean, we would take this thing minus its mean times this thing minus its mean transpose, okay? So when we do that, we're going to get an X covariance term. We're going to get correlation terms, and then we're going to have the covariance of Y. So let me see if I write this that you'd almost believe it. Sigma XX, sigma XY, sigma YX, and sigma YY, okay? So when we do the covariance of the vector, this block is just a covariance of X, this block is the covariance of Y, and then we have the correlation between X and Y. And this one is, it's transpose. So you can do that little exercise at home, or you can believe it. Now we know this, that's part of the problem statement. We just computed this, so we need to do this. So have a little bit more practice with covariance type calculations, okay? So sigma xy equals expected value of x minus mu x times y minus mu y transpose. So we have x minus its mean times, and then we just got through playing with y times its mean. It's x minus mu x, come on Grizzle, right, plus the noise minus its mean. Transposed, yay! Okay, so that's just the definition. Correlation between one vector and another vector is the vector minus its mean times the other vector minus its mean transpose expected value, okay? We just wrote down the definition. Expected value of, well, we end up with x minus mu x, and we see that transpose there, so we get x minus mu x times c transpose. And then we have x minus mu x times yep, I was right for a change, epsilon minus mu epsilon transpose. Okay, so I just expanded it out. And so this is sigma xx C transpose, and then this expectation is 0. But if it wasn't, it wouldn't really cause us that much problem. We just write sigma x mu here if we had that data. Yep. Oh, yeah. Otherwise, it's not a covariance and the multiplication doesn't make sense. Thank you. Yep. I was so thrilled to get my C transpose on the right side that I forgot that one. Anything else? Okay, so this is sigma xx C transpose and then plus 0. Okay. So let's summarize all this. Covariance of x, which is the covariance of this vector, our unknown x, our measurement of x, and that matrix is sigma xx, part of our original data. We just computed sigma xx, not transpose here, on the C. It's symmetric, so this is, no idea how that happens. C times sigma xx. And because this is symmetric, there's no transpose here, though in principle it's not wrong. Okay, and then we computed the sigma yy already, and we had C sigma xx C transpose plus the covariance of the measurement noise. Okay, so now we know all of the statistics of this joint vector are unknown, something in Rn, and then our measurement process, y equals cx plus epsilon. Okay, are we good? Here's our Mve problem. We know initial data on how x, the uncertainty we have in our robot's position. We have a probabilistic description of the uncertainty of our LiDARs and cameras and things like that. And then right now I'm trying to build the statistics of how x is related to the measurement process, y equals cx plus epsilon. And so now I have that. I had to construct that from the data. The mean, that's easy. And the covariance took us some grungy calculations, but it's straightforward once you just write it down and just expand it. Okay. Now, what I want to compute next I want to compute x given y equals some value. Okay, so let's review that. I know you guys all worked the homework problem, so you've studied that part of the Gaussian random variable handout. But just to refresh your memory, since it's maybe been a long time since you worked it because you did the homework, who knows, on Friday of last week or something. Okay, so I'll just refresh your memory. Okay, so this is fact 1. Okay, so here's the notation. We take a Gaussian random vector with two different vectors in Rn and Rm. So for us, that's x and y. The means here are denoted mu1 and mu2, and then we have the covariance matrix of the joint density of x1 and x2 that's been partitioned into the covariance of the one vector, the correlation transposed, and then the covariance of x2, okay? That's just like what we have. So that was just notation. And so here's the key thing. The conditional density of x1 given x2 is measured to have value x2 is the conditional mean is equal to the mean of the first process, x1, the correlation term, the information matrix of the measurement, times the measured value. You're looking at its difference with respect to the mean. Okay? And then the covariance of the conditional covariance of x1 given x2, and this is where we know we're not increasing the uncertainty, is sigma 1, 1 minus this. Now this is a positive semi-definite matrix, so if you multiply this and this times any number and it's transposed, you get this number, and then you're subtracting off this, and it will be non-negative. Okay, so this matrix is smaller than this one because we're subtracting off a positive semi-definite matrix. Okay, all of its eigenvalues are smaller. So that's the covariance, conditional covariance. Now, you got them written down? You memorized them? Let's apply them to this problem here. Okay? So here's our covariance, and sigma yy, there it is. C sigma xx, C transpose plus sigma epsilon. Okay? So, x given y equals a number is distributed with a normal random variable, which is going to have a mu x given y and a covariance of x given y. The mean of x given y is equal to the mean of x plus the correlation, and that was sigma xx C transpose. Let's peek up and check. Sigma xx C transpose, that's the correlation between x and y. Okay, times the information matrix, so we go C sigma xx C transpose plus sigma epsilon epsilon inverse times the measured value minus the mean of y. Okay, so x given y is now shifted our best guess of where x would land. A priori, only thing we can say about x, our best guess was the mean. We've now shifted it by this measurement. So how the measurement ended up being different from its mean value times the information matrix. So if x and y are uncorrelated, then this thing would be, that's the information matrix of y. So if y is very, very, very noisy, then this is very small. And if y is very clean, then this is very big. And we're going to really take that information and make a big change with x. And then it's scaled by how x and y are correlated. So this is sigma xy when we have this. That's the correlation. Okay. And then the covariance of x given y is the shear complement. So it's sigma xx minus sigma xx C transpose times C sigma xx C transpose plus sigma epsilon epsilon inverse times C times sigma xx. And so by making the measurement, we've shifted the mean of x, and we've reduced the uncertainty, by this amount. Okay. So that's the minimum variance estimator. our solution, this was 0, okay? This was 0, and this is k times y, okay? This is p c transpose c p c transpose plus q times y. And then this was the covariance of the estimate. It was the original variance of the state, and then minus this quantity here, which we recognized as a sure complement. But now we see where it comes from. Yes. Help? Conditional random variables are still random variables. They have mean and variances, and so that's how they work. Questions on that? If we have this, the Kalman filter is going to be like falling off a log. Really easy to do is what falling off a log means in English, okay? No? Thumbs up I got. How many thumbs up for moving on do I get? Nobody wants to do it. Question, thank you.
I'm trying to think through what happens if that variance of the measure of the noise is the identity matrix.
Okay. So if this one here is the identity matrix? Yeah?
Then what do we
So that's a nice positive definite matrix. Yeah? Put a constant in front of that identity and just make it bigger and bigger. This inverse will go to 0. Okay? And we will not reduce the uncertainty in x. But put this as a constant times the identity and send that constant to being very large. This becomes 0. And I don't care what we measured, we're not budging on our estimate of x. It does what you know has to happen, but what you don't know how to have happen with intuition is how to adjust the gain, how to respect the information you've been given by making that measurement y equals cx.
So the covariance is independent of our measurement.
Yeah, so this is the thing for a Gaussian random vector. The covariance is the sure complement and it has nothing to do with the measured value. In general, you know, this density depends on x2, and when we calculate the covariance, we would expect it to depend upon x2 as well. So in general, it does. For Gaussian random vectors, the covariance is magically independent of the measurement. It's just the mean that shifts. Okay. So if we measure a larger x2, it doesn't change the variance. Okay. That's just the way the Gaussian processes work. Okay, so we had a model, y equals cx plus epsilon. We took statistical description of our current best knowledge about the position of our robot. We have a measurement process, our knowledge about our sensors. We use that information then to say, now we make this measurement, what does that change about our knowledge of where the robot is? And so we calculated how the mean would change and how the spread about the mean changes due to making that measurement. It's profound, okay? It's cool, it's profound. Okay, so if you're good with two things, x block 1 condition on x block 2, let's do 3 things now, then we stop. We don't do 4. I'll leave that for you on the final exam. No, I wouldn't do that to you, okay? I promise. Okay, so let's go back to the part that's related to the homework problem that you worked. So if you worked the homework problem, you verified that x conditioned on having both components known is the same as taking the distribution of x conditioned on y, y conditioned on, x x conditioned on z, y conditioned on z, and then conditioning those, okay? So, for us, in the Kalman filter, x is the state of our robot, y is the current measurement, and z is all of the old measurements, okay? We really want to get our best guess of x with all of the measurements, but we don't want to process it like that because that is a batch process. That's batch. And the Kalman filter notation is super cool. This gives us the conditional mean of x at time k given all of the measurements up to time k. And this is the conditional covariance. So this is what we're after, x conditioned on all of the measurements, y0 up to yk. This is a conditional covariance of time k given the measurements up to time k. Now, the way the recursion will work is that we will be able to have x conditioned on the old measurements. So this is going to be our best guess of x at time k conditioned on all but the current measurement. We're leaving that one out, but we don't have it yet. It will have a mean and a covariance. Now the measurement depends upon x and a noise process, and it will also have a mean and a covariance. Just wanted to make sure it wasn't me, but I left my phone in my office. I realized, no, it's not me, okay? Could have been, could have been. So we will calculate the conditional density of y at time k given all of the measurements up to time k minus 1. And that will just be c times the conditional mean of x at time k given all the measurements at k minus 1. And then it will be c times the covariance of x at time k given k minus 1 c transpose. And then this is what your homework problem showed, is that once we have the joint density of x given y and z given y, then we can compute this whole thing, okay? And that's wrong. That's x given z. That's x given z, and this is y given z. Okay, z is the old stuff. And it's x given z. Oh, I've got it written down here correctly, okay? So once we have this information, we do one conditional, we do this vector conditioned on knowing the value of this random variable, and we get the entire we get the statistics of x conditioned on all of the measurements. Okay. How many of you really did this and got the same answer? 4 or 5 or 6 of you? Were you surprised that it came out, or just confident, or?
I was surprised. I don't really get the intuition.
Yeah, it's hard, okay? It's hard. But it's a general fact. It's a general fact. Let's go back really quickly to the derivation. Oh, that's not the derivation there. It's right here, okay? X, y given z, which really means x given z, y given z. So the joint density of that and then we condition on y given z. But this is a conditional density, so it's the joint divided by the marginal. This is a conditional density, it's the joint divided by the marginal. And then this and this cancels, and you see it's the joint of all three of them divided by the marginal of all of our measurements. So it's the state with all of the measurements divided by the marginal of all of the measurements. But it seems like a trick, okay? Okay, so you probably want that one written down on your cheat sheet for the final. Okay, so let's look at the Kalman filter in our remaining moments. Okay, so part of it looks like our Mve problem, y equals cx plus noise. Okay, this is kind of the standard notation you will see. They don't put epsilon when we're doing the Kalman filter and stuff like that. Okay. So it has linear dynamics. There's a noise term on the state, which represents your modeling uncertainty. And maybe that's coming from the terrain, your robot's moving on some lumpy ground, so your physics isn't perfect. Maybe it's coming from wind gusts, or maybe, you know, your model parameters are not exactly what you think they are. And so you try to cover the uncertainty in your model by saying, it's not exact, okay? That's what this is doing, not exact. And then this is the measurement process, and you guys are kind of used to seeing CX plus noise, so I don't have to justify that one. So what are all of the random variables in this problem? The unknown initial condition of the robot, the noise terms entering into state, and the noise terms entering into the measurement. So the basic assumption here, in the simplest of all possible worlds, is just like we did with MVE, where we assume the correlation terms are zero. Question?
What's your input?
There is no input in this one. You can just add it because it's deterministic, but right here, it's just a drift. There's no BUK, but if you want to add one, it changes nothing. And then we have noise, etc. Yeah, so it's not a control problem, but it should be because we are roboticists, okay? Or control engineers, or ME students trying to get math credits and graduate, or whatever we are, okay? So the assumption is, just like we had an MVE, the state is not correlated with the measurement noise. Also, it's not correlated with the process noise, and this noise is not correlated with that one, okay? So all of those things are uncorrelated, is the assumption. So when you stack up the initial condition and the measurement noise and then the state noise, and you look at their covariances for different times and everything, you get all of the cross terms are zero, and even the correlation of, say, the measurement noise at time 2 and the measurement noise at time 3, that's assumed to be zero as well. So one reading of the sensor, whatever noise process is affecting it, you get an independent value when you grab the next one. So that's what these delta KLs, it's the Kronecker delta. They're 1 when K equals L and 0 when not. So almost everything is uncorrelated in terms of the noises. Now, the measurement is correlated to the state through this linear model, okay? And that's the same calculation we made with MVE. So you can read through all of these. Okay, so remember xk plus 1 is a matrix times xk plus the noise processes, okay? So x1 depends upon x0 and w0. x2 depends upon x0, w0, and w1. etc. And so xk will only depend up to wk minus 1, because xk plus 1 depends upon wk. So xk as a random vector is also uncorrelated with wk. They're independent. And you get the same thing with the measurement. Y is c, etc. And the noise process at time k is uncorrelated with the states. They're independent. So that's stuff you deduce from the previous set of things. So it's just, you don't have to make those assumptions, but for us, it's good enough. Okay, so we've seen these definitions. We're pretty good with them. Conditional mean of the state at time k given the measurements at time k, the conditional covariance, the conditional mean and covariance of the state given the measurements at time k minus 1, or it's the same thing as looking at x at k plus 1 given k. Okay, just shift k by 1 has a mean and a covariance. So we have data on the initial conditions, and so here's the Kalman filter. It's this loop. First thing we do is we take our conditional mean k given k minus 1, we get a new measurement, and we update it. And then we update the conditional covariance. Now we've used the measurement. Now we use the model, and we predict forward what's going to be the mean of x in the future. And then we calculate the conditional covariance of that. So, okay. Now we go back. We get a new measurement at time k plus 1. All of these are k plus 1s, and we update that. Then we predict forward. We just go on and on like this, okay? So this is the most interesting one, the measurement update. The time update is the easiest part. So let's focus on the measurement update. Now, what does that look like to us? I mean, conditional mean at time k is the conditional mean at time k given k minus 1 plus the correlation matrix times the information matrix times the measured value minus the mean of y at k, okay? That's all it is. It's MVE. Here's the conditional covariance. It's the sigma 1,1 term minus the things you have. So you put k here, you get, this is the shear complement. So this is just MVE if we understand what are the statistics involved in this. But it's just MVE. It's the exact same formula we just derived laboriously, okay? This is the correlation between x and y, the information matrix of y, etc. So we should be able to understand it. Hang in there. Okay, so here's big YK is recursively related to the current measurement and the past measurements, and these are all the definitions we've seen several times. Okay, so here's the proof. It's by induction. Okay? So the base step is our best guess of x given no measurements, because they started at time 0, is just the mean of 0. And our initial covariance is just the covariance of x0. Okay? So now, induction step. Suppose we know the conditional mean of x given the measurements up to time k minus 1 and the covariance, okay? We want to derive the conditional mean at time k, given all the measurements at time k and its covariance. And then we want to do the one step forward. So let's focus on this part. Okay, so this is what we're after. Okay. So that is simply the mean and covariance of xk given capital Y. Okay, that's all of these guys, okay? So we use our trick of writing this as xk, little yk, big yk minus 1, and get x conditioned on the block is x conditioned on yk minus 1, and the measurement conditioned on all of the measurements up to time k minus 1. Okay, so we need to do this conditional, we need to calculate this conditional random vector. Okay. So just like we looked at earlier, we're after, and if we can compute xk, yk conditioned on yk minus 1, it's all over. And this is just like what we did for MVE, where we computed all of the statistics for x and y, and then we did x conditioned on y. Except now it's x conditioned on yk minus 1, conditioned on yk given yk minus 1. Okay? So this is just xk conditioned on yk minus 1, conditioned on yk given. Okay, so if I can compute the joint density of xk and yk this, then life is good.
They're not equal though, right? You just get what you need.
Yes, excuse me, this is what I need. Okay, I need the joint density of this. You're right, okay? I need the joint density. Okay, so let's figure out so x given yk minus 1, that's part of the induction step, okay? This is x given yk minus 1, its mean and its variance. So we have that as part of the induction step. What we don't have is this, so I need that. Okay, so the measurement is linear. So yk conditioned on yk minus 1 is c times xk conditioned on yk minus 1 plus the noise term conditioned on yk minus 1. Okay, so that's just using linearity. So I'm trying to calculate the statistics of yk this. And so the mean is now extremely obvious. The mean of this is just ck times the mean of this. So that's ck x hat k given k minus 1. Vk is independent of yk minus 1, so Vk conditioned on yk minus 1 is just Vk, and it has 0 mean, okay? So calculating the mean of y given k minus 1, it's just ck times the mean of x at time k given k minus 1. So that part is easy. Doing the covariance, this is exactly the formula we had doing the calculations in the MVE. Okay? The covariance of yk given yk minus 1, it was ck times the covariance of x, so it would be x at k given k minus 1, and then the covariance of the noise term. correlation between x and y, these two conditional random variables, it's the exact same formula as in the MVE. It's the covariance of the x term times C transpose. And the only reason we have K's on the C's and stuff is that our model is super, super general. We're allowing A to be time varying. Where is the model? It's way up here. We're allowing A to be time varying. We're allowing C to be time varying. How the noise enters, because it doesn't change anything. But for many applications, those guys would be constant because it's really hard to give an infinite number of measurement models. It's really hard to get an infinite number of state models. Okay, so. So just like in MVE, we compute the mean of x and y. Only thing different is this is the mean of x and y conditioned on the old measurements. We get what we were started with in our induction step, the mean of x at time k given k minus 1. And then the mean of y is just ck times that. And then we calculated the covariance matrices of x given to us. We calculate the covariance matrix of y given k minus 1, and then the correlation terms. And so once you have this, it's the same formula that we applied to solve the MVE. And this is our formula from the minimum variance estimate. The mean after you've made a measurement of y, you take y minus its mean, you take the mean of x, and then you've got the correlation matrix times the information matrix of the measurement process. And then the covariance is the Schur complement. So it's the original covariance, and so this is really MVE. Okay. I'm going to skip the measurement update because that's really short. I'll let you go through it if you want. It's by far the easiest. The hard one is the minimum variance estimator. What I want to spend the last couple of minutes on, if there's questions, but also going through and saying, you're responsible for this, okay? And you're not responsible for this, okay? Sound fair? What do you have to know? Everything. That was easy. Okay, so the Kalman filter, see? Where's the Kalman filter? Even I lost it. Key idea, filter derivation, preliminaries, there we go. Okay. Know this, you do not have to know how to derive it, okay? Know this. It's nice to know the derivation, but you don't have to. If you look through this, this is a form of the Kalman filter that is what most people implement. They don't separate out the measurement update and then the time update. They combine them into one overall equation, and look, here I put a control. Okay? So know about it. if you need it on the final, I will give you the equations, okay? So don't bother putting it on your cheat sheet. Okay, so this will be posted like this. I can't go backwards on it now, okay? I want you to be aware of it and just to think that there could be possibly like a true-false question or something like that, just so when you get into another course, I'm not treated like an idiot, that's all, okay? It's only for my own reputation that I'm asking you guys to be aware that this is typically how the Kalman filter is written down, with you're propagating the conditional mean, you're propagating the conditional covariance, and from that you're getting what's called the Kalman gain here. Okay. And I think one of your homework problems will have you use that as well, okay? Now let's go to the handout on Gaussian random vectors. So this one, no, okay? Not important. Fact 2. No, we did this calculation, okay? We had y equals cx plus noise, and we calculated this, except we didn't have a matrix here, okay? This was our C sigma xx C transpose. We did this, so know that. Okay, yeah. Know what a random variable when it's normally distributed is. I really don't care if you know the formula for the density. Just only thing I want you to know is that it depends on two quantities, the mean and the covariance matrix. So he's got an inverse, we call that the information matrix, but it's the mean and covariance. So know mu and sigma define x normal. Okay, that's all I care about. I don't really care about the formula. So if you believe it's the mean vector and the spread, that's all you really need, okay? The marginals, it's too useful not to know that you just read them off the diagonal. So the marginals, you just get off the diagonal terms. And then these two facts, really quick. If vectors even are uncorrelated, then they are independent. So for Gaussian, uncorrelated equals independent. For general random vectors, uncorrelated does not imply independence. It's only it's Gaussian for sure, okay? So know this. And so that's just a fact to memorize. We haven't proved the independence. The linear combination, we did this calculation today. Okay, this was C times X plus the noise term. Okay, so we did this exact calculation. We did all of the covariances, et cetera. So it doesn't require it to be Gaussian for those two things. So that's it. Okay? So know the conditional distribution, you'll need that. And then of course from your homework, you'll want that what happens when you have the three components. So, fair enough? It's a lot, but recursive MVE is what the Kalman filter is all about. Just recursive MVE. Okay, any questions? No? Happy? Happier than when you came in because you're smarter? You feel heavier because of that knowledge or lighter because you are enlightened? Which do you feel? I feel heavier because now he expects me to be able to do something with this knowledge. Okay, so in your homeworks coming up, you'll take the inverted pendulum on a cart and build the Kalman filter. It'll be kind of cool. Question, yes?
So with blue, we assume a fixed state, right? Where x is not.
Yes, so blue, y equals cx plus noise, x is deterministic, and x is equally likely to be anywhere.
So I don't remember that. What was there an assumption that was?
Minimum variance estimation, we have a covariance for x. We just did it today where there was a mean as well, but it's in the basic problem, it's just zero mean, x has a covariance. Y equals cx plus noise. The noise has a mean, we assume zero, we did today non-zero, and has a covariance. So MVE, there's two random variables, x and the noise. Blue, there's one random, vector. X is deterministic, not random, equally likely anywhere in Rn, and the noise has thing. And then there's weighted least squares, which is what you're doing there, is assuming that you have no knowledge of where the uncertainty comes from, and you just go, you choose a weight matrix. And so blue says choose the weighting matrix as the information matrix of the noise. So the information matrix is big where the noise is small in those directions. Yep.
Okay, so then the Kalman filter is then also combining the knowledge you have of your model. That's like the next step.
So the Kalman,
They're all connected.
yeah, so the Kalman filter, so RLS is recursive weighted least squares. That's all it is. So there's no randomness at all, and this is zero, this is zero, and AK is the identity. X0 is unknown, but we have no distribution for it. So recursive least squares, X is a constant because this is the identity matrix. Okay? You could, I guess, I don't know if you can do recursive blue or not. The Kalman filter is just recursive minimum variance estimation because we keep getting new measurements. And now the difference is we are allowed to have X not moving. But you could go back and put this as the identity, and X only drifts around from noise if you wanted, and look at that version of the Kalman filter. And then that would be recursive exactly what our MVE looked like, what we did in class, because we had y equals cx plus v, and x wasn't changing. So actually, this is zero, A, the identity, you could just do recursive MVE with no dynamics. And then the Kalman filter allows X to evolve.
So yeah, there's like
Yep, so X is now moving, our robot is not stationary anymore, and we're not just pinging the same measurements off the wall, okay? We're changing our perspective of the world. And as we're moving, we're updating our best guess. When I'm reporting to NASA where the rover is, okay, you know, I'm the Mars rover and I'm uploading my position, I'm giving better information based upon the measurements I have. But if I'm just parked, then the Kalman filter reduces down to doing recursive basic MVE, which is then similar to recursively squares, where you had no dynamics either. Yep.
Heard something called like a white noise model before. So
Yeah.
that's just all these assumptions then.
So, yeah, so if you take the Fourier transform of processes where they are uncorrelated, their spectrum is flat, they have all frequency components, and that's where the term white comes from. Okay, so if you do the Fourier transform of your noise process, all of the frequencies are there. If it's shaped, then the noise is called colored, because then you get blue and green and red and all those other, and all the other different things, okay? Then the noise terms are correlated, and so there's extensions of the Kalman filter that handle that as well. As you can imagine, it's a little bit more complicated, but if you understand this one, you can go read the paper if you need it. But we're not going to cover it in class. Just I try to do the basics, focus on the key points, and keep showing estimation in many, many different forms until it finally sort of takes hold, I hope. That's what I'm hoping on. Okay, we're over time. Thank you. And apologies again for not having the mic on at the beginning. I'm apologizing.